Talk is about indium gallium nitride photovoltaics with bandgap, polarization, and doping grading. C.Jayant Photonics materials. So we talk about the physics of solar cells made from the indium gallium nitride alloy system with materials grading like bandgap grading, polarization grading, etc. Slide here shows the wavelength and energy range of indium gallium nitride. For example, you can see in the figure on the left that the indium gallium nitride alloy system covers the entire energy range from the infrared to the ultraviolet through the visible. Actual alloys have some bowing, but this plot gives a very good idea of how the bandgap energy of this alloy system varies. The bandgap of indium nitride is about 0.7 to 0.8 electron volts, and that of gallium nitride is 3.4 electron volts. And also in the same series of semiconductors is aluminum nitride, which has a bandgap of 6.2 electron volts. Now, we do not consider aluminum gallium nitride alloys in this talk. However, there are quite a few devices of different kinds that can be made from the aluminum gallium nitride system as well. And you can also see in the plot the effective mass variation with the lattice constant. And you can see that the effective mass has the same kind of trend as the bandgap. And now that is consistent with the K dot P theory for effective mass in terms of the conduction band states and the valence band states, etc. So the thing to keep in mind is that in indium gallium nitride alloys, when the gallium percentage is higher, the effective mass tends to be high. Now, effective mass affects quite a few material parameters like mobility, etc. And our mobility affects the current flow in devices. And since we need charge carriers to flow in a solar cell in order to get currents and voltages out of it, these effective masses also have an impact on device characteristics. Now, thing to mention here is that graded devices are ideal for capturing solar radiation with minimum losses to the lattice. And we will discuss more of that kind of physics later on in this talk. This slide shows a comparison between the indium gallium nitride semiconductor system and other similar semiconductor systems. For example, it shows the group 3 arsenides and the group 3 phosphides as well. So you can see that the group 3 nitride system spans the entire energy range from infrared all the way to ultraviolet to the visible, while the other material systems shown here span only part of the visible range and then the infrared. So clearly for solar cell applications where the solar cell spectrum itself spans the range from infrared to ultraviolet, the indium gallium nitride system is very useful. And the other thing that is shown here are that these dotted lines basically represent indirect bandgap materials. Now, the indium gallium nitride, the group 3 nitride system is a direct bandgap semiconductor system, and that is very good for light absorption, and that helps to optimize solar cell devices better and other kinds of devices better as well. While the indirect bandgap systems aren't that ideal because the absorption coefficients tend to be low and the device dimensions have to be much larger, and that hampers device optimization. Also shown in this plot are indirect bandgap silicon and germanium. So you can see a comparison between these material systems and see that the group 3 nitride system is clearly well suited for photovoltaic applications or solar cell uses. This slide shows the nature of solar radiation, basically the photon power spectrum in solar radiation. It shows the solar radiation both in outer space beyond the atmosphere of the Earth and also at the surface of the Earth after absorption by molecules in the atmosphere. So there are diatomic, triatomic, and other kinds of molecules in the atmosphere which absorb solar radiation, and they absorb solar radiation in specific bands. They absorb photon energies in very specific bands, some in the ultraviolet and some in the infrared. And you can see here that that manifests in the spectrum received at the surface of the Earth, what is shown as AM 1.5G radiation here. You can see that those absorption bands cause these dips. So there are these dips at specific bands. And the exact nature of the spectrum needs to be taken into account while optimizing solar cell devices. An important consideration here is that when photons of specific energy are incident on the solar cell from one side, there is a change of dielectric function or dielectric constant from the air to the semiconductor material, and that leads to reflection. So some of the photon energy is reflected and some of it is transmitted into the semiconductor and is later absorbed inside the semiconductor to some extent, or maybe a lot. But we clearly need to reduce the reflection of photon energy in order to get good solar cell efficiencies. And so the photon reflectivity makes it necessary to use anti-reflective coatings. Now, these anti-reflective coatings are achieved by doing dielectric constant grading kind of thing, because that reduces photon reflectivity and makes sure that most of the photon energy actually gets into the semiconductor in order to cause photocurrents and solar cell action. Also to keep in mind is that there are electrodes in the solar cell because the photogenerated currents need to be collected, and so you need electrodes in order to get currents and voltages out of the solar cell. Now the electrodes typically made of conducting metals or conducting material, and have to be made of conducting metals or conducting materials, and these tend to reflect and also to some extent absorb radiation. And we need to have transparent conducting electrodes in order to reduce the electrode absorption and reflection. And so these work by having the right spacing between the plasma frequency and solar radiation. So the idea is that the dielectric function of the conducting electrode is a function of frequency, and it depends on the plasma frequency, and it actually goes from negative to positive as we vary the frequency. And what we need is that the plasmon frequency needs to be lower than the solar radiation frequency in order to make sure that the solar radiation isn't reflected much. And that is why we want to use properly designed transparent conducting electrodes to get good solar cell operation. This curve, in this slide, we talk about the physics of the currents generated in the solar cell. Current voltage curve, or the IV curve of the solar cell under illumination, is given by this equation here. You can see that there is a current density, and that has a short circuit current density component, a dark current component, and there is an eta, or the so-called ideality factor, in the solar cell. Now, in order to get good power conversion efficiency or energy conversion efficiencies in the solar cell, we need to make sure that the short circuit current is large, and also we need to make sure that the dark current is low. And these requirements lead to some design constants, as we'll see. Now, the short circuit current is typically maximized when you lower the band gap, because when you lower the band gap, then more of the solar energy can get absorbed from the valence band into the conduction band. And now this lowering of the band gap can be structure dependent because you can have material grading or band gap grading that may be required in this kind of structure. Now, I dark is minimized, made less by having wider band gap. So you can see that these two requirements are pulling in opposite directions. That means you need to do both. And that means, so you have to use a combination of wide and narrow band gap within the same structure to increase the conversion efficiency. Now, how do you do that? What you have is you do material composition grading. That means, for example, as the solar radiation is incident from the, let's say if it's incident from the top in the solar cell, what you do is you have one composition close to the top of the solar cell, and you vary that composition as you move away from the top of the solar cell. And you do it in such a fashion that you achieve these dual goals of maximizing short circuit current and minimizing the dark current. Now, the eta is an ideality factor that is typically affected by, for example, non-radiative recombination at, say, dislocations or at defects. Now, there are dislocations in these materials. For example, there are threading dislocations, which are like missing lines of atoms, and there are vacancies in thermal equilibrium or even in non-equilibrium. And these introduce what are called deep states or mid-gap states. That means these are states deep inside the band gap of the semiconductors. And these affect the ideality factor of the diode because they cause non-radiative recombination, which enters into the current voltage equations of the device. And and we typically like an ideality factor that is as close to 1 as possible, but in practice, the ideality factor tends to be larger than 1. And we want to keep it close to unity in order to get good solar cell operation. This slide, we talk about more about the short circuit and dark current optimization using the combination of wide and narrow band. Now, when we use the combination of wide and narrow band gaps, there are some added complications like barriers to current flow. So a very careful optimization is needed. What do I mean by that? Well, for example, you can say that if I do composition grading, I may digitally grade the composition. For example, I may have one composition close to the top electrode of the solar cell, and then I move to another composition. And I can do that abruptly, or I can try to do it more gradually through a kind of gradual grading. And you can see that the abrupt grading may have some uses, but it has some complications in current flow. And so we need to understand whether we need quasi-continuous grading or whether abrupt grading is possible. So the possible structures for solar cells made from indium gallium nitride are, for example, double heterojunction structures, graded layer structures, and multi-quantum well absorption layers. Now, we talk mostly about the second type of structures as the graded layer structures in this talk. So in the graded layer structure, we typically do a quasi-continuous type grading of indium gallium nitride, and you optimize the device grading to achieve the highest power conversion efficiencies from this device, and the highest quantum efficiencies from this device. The double heterojunction structure is basically the kind of abrupt junction that I mentioned previously. As I said, that has some complications due to current flow barriers, and we need to optimize those if we are using a simple double heterojunction structure. The thing to keep in mind is that while one kind of device structure may be much better from the device characteristics perspective, the fabrication or the epitaxial growth of the layers needed to make this device can become more complicated. So the technology can become more complicated. So you need to find a balance between the technological complexity and the device performance. So we talk mostly about the second type of the graded layer structures, but we have to keep in mind that it may be possible to optimize the double heterojunction structure with a less complex fabrication or epitaxial growth procedure. And the third category is the multi-quantum well absorption layers. We do not discuss those much in this talk. However, it is possible to have multi-quantum wells in the absorption layer. What do I mean by that? Well, the multi-quantum wells can basically change the electron states and the hole states that are there through quantum mechanical equations. And that leads to a modification of the absorption characteristics of these layers. And when you modify the absorption characteristic, you can basically modify the requirement for example, device dimensions or device widths or layer widths. And that can lead to some better optimization of the solar cell characteristics. However, you have to keep in mind that again, from the device fabrication perspective or the epitaxial growth perspective, the multi-quantum well requires many quantum wells to be fabricated, and so it's a more complex fabrication procedure. So we have these trade-offs between device performance and device fabrication complexity, and we need to keep those in mind as we design our solar cells. So a brief word about the epitaxial growth procedures that can be used. For example, there is molecular beam epitaxy, there is metal organic chemical vapor deposition, and then there are some other kind of epitaxial growth mechanisms as well. So they are all to be considered while deciding which is the best to use for the specific solar cell structure that we are trying to build. Slide here shows the typical structure of one of these indium gallium nitride solar cells. It has several layers. The layer shown in red here is basically the major light or photon absorption layer and a drift. So the photons are absorbed in this material, and the generation of conduction band electrons and valence band holes. We want these photo-generated electrons and holes to drift under the influence of an electric field, and that is the so-called drift layer. Now, where does this electric field come from? Well, there are built-in electric fields in semiconductor devices. For example, if we have an N-type doping on one side and a P-type doping on one side, we can have a so-called depletion layer, which has a built-in electric field, and that can be the drift layer that we use in these solar cells. Now, on both sides of the major absorption and drift layer, we have some dark current reducing layers. So these are the layers where we may have to use a different kind of band gap composition in order to get best device characteristics. Now, in this diagram, incident photons from solar radiation are incident from the top. And then we also show the front contact as an anti-reflecting layer, so that most of the, and a transparent conducting electrode, so that most of the photons get into the semiconductor or into the light absorption layers in order to get absorbed and to generate photocurrents and photovoltages. So that is the basic photovoltaic requirement from these structures. Now, these different layers, as I already mentioned, have different indium and gallium composition in order to optimize the device characteristics. So in this slide, we show typical absorption characteristic equations for direct bandgap and indirect bandgap materials. So this goes into the physics of light matter interaction in these semiconductors. Now, in direct bandgap materials, close to the bandgap and above the bandgap, the absorption coefficient depends in a square root fashion on the incident photon energy. It's basically square root of the photon energy minus the band gap energy and times some constant. And the absorption coefficient in indirect band gap materials, when there is phonon absorption, is or phonon emission, is basically given by the equations shown here. Those absorption coefficients in indirect band gap materials tend to be lower. So indirect band gap materials need phonon-assisted photon absorption. Those absorption coefficients that are lower, and they have different device optimization. Now the direct band gap materials have intrinsic photon absorption. Now these indium gallium nitride alloy system is all direct band gap, and they have intrinsic photon absorption and that. The thing to keep in mind though, that if the photon energy is much higher than the band gap, then it may no longer follow the square root dependence. If it is much higher than the band gap, then it can have a much more complicated dependence on energy. So the physics here is that the absorption coefficient depends on the so-called joint density of states between conduction band states and valence band states. And this joint density of states reflects the complexity of the conduction band dispersion at all kinds of energies, and the valence band dispersions are all kinds of energies, and that can have all kinds of structure. And for example, it can have Van Hove singularities, etc. One other thing is that since the indium gallium nitride alloys are getting used, we need to keep in mind that indium nitride is direct band gap and gallium nitride is direct band gap. But what about the alloys? Now, for low level of alloying, that means when it's mostly when the gallium percentage is high or when the indium percentage is high, you can expect that it will still remain direct band gap. But what happens at high alloying? It turns out that in these materials, it is direct band gap all the way through. This may not be the case in all kinds of alloys. For example, at high levels of alloying, the electron states can change not only quantitatively, but also qualitatively. And similarly, the valence band states can also change qualitatively and not just quantitatively. And when there is a qualitative change in the nature of the conduction band states and valence band states, the nature of absorption can change. So all that needs to be kept in mind as fundamental physics considerations that must be used to optimize device design for these solar cells. This slide shows absorption coefficients as a function of photon energy for different material systems. We have direct band gap silicon, direct band gap gallium arsenide, and then we have indium gallium nitride of different indium compositions. So we show 4 different indium compositions in this figure. You can see that as the indium composition decreases, the absorption edge gets pushed to the right in photon energy. And you can see that with lower gallium composition or higher indium composition, you can start getting absorption starting from the infrared itself. And you can see that you can get fairly high absorption coefficients of 10 to the power 5 per centimeter in the infrared and visible range, and you can even go to much higher absorption coefficients as you move to the ultraviolet. So this makes the indium gallium nitride system well suited for doing solar cell designs and solar cell optimization. And these absorption coefficients can be calculated, and also they can be measured. For example, there is the complex dielectric constant, which has a real and an imaginary part, and the absorption coefficient is related to the imaginary part of the complex dielectric constant or the complex dielectric function. And so we can have comparison between theory and experiment so that we can calibrate our band structure calculations to experiment also if needed. And we get fairly good agreement between experiment and theory for this kind of absorption coefficient. Shown in this slide are different recombination mechanisms that are operational in these solar cells. For example, there is this called radiative recombination process, which basically like a mass action law between electrons and holes. On the left here, we show a so-called Shockley-Reed Hall type of non-radiative recombination effects, that is trap mediated or deep state mediated, that is mediated by defects in these materials. And then we have the 3 carrier kind of Auger recombination mechanisms. And all these, the total recombination rate is the sum of all these recombination mechanisms. Now, when the photons are absorbed and they generate electrons and holes, we want these electrons and holes to drift and then to get collected at the electrodes, where we don't want them to recombine, because if they recombine, they don't contribute to the photocurrent, and that decreases the solar cell efficiency. So what we have here are these recombination mechanisms that need to be minimized. One thing to keep in mind that radiative recombination is qualitatively different from non-radiative recombination, because radiative recombination again generates an above band gap photon. That means there is basically re-emission of photons, and then that photon can be reabsorbed. So to some extent, some of that recombination loss can be recovered because of reabsorption. However, the thing to keep in mind is that radiative recombination, it doesn't occur in the same direction as the incident radiation, and it is random in direction. So some of the re-emitted photons can be lost. So we should try to minimize all kinds of recombination processes, but specifically we should try to decrease the non-radiative recombination rates in these devices. Here we show surface recombination that can happen due to deep states at the surface, which is given by this integral. And then we have the drift current of holes and drift current of electrons, which are given by these equations. And then there is also diffusion of electrons and holes in some layers in these devices. Then we have the continuity equation for holes and continuity equation for electrons. And then we have the electric field profile equation given in charge densities in these devices. So these are the electrostatic and electrodynamic considerations that enter into deciding device characteristics. In this slide, we show the continuity equation with the hole and electron drift and diffusion equations put in, and then we have the generation rate due to the absorption of incident solar radiation, and we have the recombination rate, and the recombination rate is basically due to all the different recombination mechanisms that we discussed in previous slides. And we need to solve these device equations for the specific kind of incident solar radiation to get the photocurrents and photovoltages out of these devices and to optimize it to get the best solar cell power performance or current voltage performance. So here we move to a tandem indium gallium nitride solar cell design. Now we mentioned band gap grading in these solar cells to achieve good device characteristics. So we basically grade the composition from the top electrode downwards in achieve the good photocurrents and photovoltages. But there's another design possible, and that is to have different subcells and put them in tandem, and each subcell has a specific composition of indium gallium nitride. And we have wider band gap indium gallium nitride, and then lower band gap indium gallium nitride, and then further different band gap indium gallium nitride. And we put them in tandem. And what we want is that each subcell absorbs a specific portion of the solar spectrum radiation and generates photocurrent photovoltages, and the net effect of all these when they are put in series is what consists the total solar cell. So we show here there is a major light photon absorption layer and a drift layer, and then the darken reducing layers, and then the front contact TCO and anti-reflective layers. But then we repeat this structure with another indium gallium nitride composition, and then another, and then we have 3 or 4 of these subcells in series. So that is the tandem concept. And what this means is that each component focuses on a specific portion of the solar cell spectrum and tries to convert all of that solar cell spectrum into useful photocurrents and photovoltages. Now, the dark currents, the short circuit currents, and the fill factors of each of the cells in the tandem cell must be optimized to obtain high power conversion efficiency or high energy conversion efficiency, as we mentioned. So this is an alternative to the single graded band gap design that we mentioned. Here we talk about the crystal structures and some basic physics that arises out of the nature of the crystal structure in these materials. So here we show gallium nitride. The green circles are gallium, although they are actually larger in size compared to the red circles. This is just a schematic, so that's not shown here, but think of the green circles as, the red circles as larger. The red circles are larger and are gallium atoms, and the green circles are nitrogen atoms and are smaller. So these larger red atoms, there is a vertical bond, and then there are bonds at angles to the vertical. And this is the hexagonal woodside crystal structure, which is the most common for these indium gallium nitride materials. Now the vertical bond is longer than the bonds at angles to the vertical. And that basically contributes to the spontaneous polarization in these materials. And we need to mention that there is also a zinc blend or cubic version of these semiconductors. And these semiconductors, when they are in the woodside structure, they have spontaneous and piezoelectric polarization, but the cubic or zinc blend version doesn't have spontaneous polarization. Thing to keep in mind is that technologically it is easiest to get the woodside crystal structure, and much more growth optimization is needed to get cubic structures. So we to some extent we need to build more of our devices using the woodside structure. And so those are things that need to be kept in mind for device optimization and also for further studies of growth optimization in these material systems. So here we show some typical directions and magnitudes of spontaneous and piezoelectric polarization for one combination of material composition. So here we show an abrupt junction between one indium gallium nitride composition and another indium gallium nitride composition. And these are the spontaneous and piezoelectric polarizations that develop in these materials. Now, there can be other combinations. We can have strained, unstrained, and compressive strain and tensile strain cases. And in each of these cases, you get a different kind of spontaneous and piezoelectric polarization effect. Air with design has to be done along with the material composition design devices. And typically one would like all the solar radiation to be absorbed and most of it to be collected as well. That means we want that the photogenerated carrier should not recombine. All the recombination mechanisms that we mentioned previously need to be minimized. Other physics and very important physics in these solar cells has to do with excitons in these materials. So excitons are basically bound electron hole states. So when the photon is absorbed and forms electrons in the conduction band and holes in the valence band, these electrons and holes have Coulombic attraction, and due to that they form bound states called excitons, and these excitons have some binding energy. This binding energy typically goes up as the effective mass of the material goes up. Now now the thermal energy at room temperature is about 25 to 26 millielectron volts. The exciton binding energy in, say, let's say, gallium arsenide material, which is a different material system, is something like maybe 20 millielectron volts, while the exciton binding energy in these indium gallium nitride materials, especially when the gallium composition is high, it can be much higher than 26 millielectron volts. It can be 50 millielectron volts. That means these excitons are kind of thermally stable even at room temperature. So these excitons are overall neutral, so they won't drift under electric field, and then the electron and hole can eventually recombine. So that isn't good for solar cell operation. So what we want is to dissociate the exciton to get the electrons and holes separated so that they can drift in opposite directions under the electric field. Now, so the dissociation is done by the electric field itself because it can cause tunneling out of the exciton state. So the exciton has a quantum mechanical state of when it forms a bound state, and then the electrons and holes can get dissociated by the electric field. So that process is key to get good solar cell performance, because otherwise more recombination will take place than drift. What we want is that there should be more drift and less recombination. So this dissociation of excitons due to electric fields is very key, especially in regions with large gallium composition. This slide shows some schematics for the dark current when there is no solar radiation, and then the current voltage characteristics when there is solar radiation. There is a so-called Shockley-Queisser limit, which is there for single junction. So when you have single junction solar cells, there is the Shockley-Queisser limit states that the maximum efficiency that can be obtained is something like 31 to 33%. These designs, with these single junction designs. But we can use the multi-junction tandem designs considered in previous slides to get higher efficiencies, and also the composition grading design can help achieve some of the same advantages. So this Shockley-Queisser limit basically is there because the photogenerated electrons and holes can lose a lot of energy to the lattice, to the crystal lattice. And the multi-junction tandem designs and the composition grading designs basically help overcome many of those losses. And that's why they can lead to higher efficiencies compared to the Shockley-Queisser limit. In conclusion, the Indium Gallium Nitride composition grading gives us large polarization induced charge distributions, and these must be considered in device optimization and device design. The cubic indium gallium nitride can offer higher efficiency. However, the woodsite structure is the thermodynamically most stable structure, and so therefore it's easier to get. It's technologically much more difficult to obtain cubic indium gallium nitride. However, the woodsite structure typically grows on the 0001 substrate, while the cubic gallium nitride tends to grow on the 001 substrate. So we need optimization of growth on 001 substrate to get good cubic materials and to get all the device optimizations that we can think of using cubic instead of woodsite. However, we need to consider both and get a good balance between the device performance and the growth and fabrication requirements. Here we mentioned some epitaxial layer growth mechanisms. For example, there is metal organic chemical vapor deposition growth. So there are the sources of metal organic compounds, and then there are the dopant sources that go and then deposit epitaxially on the substrate, and then we form the device layers. And growth conditions need to be optimized in order to dislocation densities, etc., and to get maximum photocurrents and photovoltages out of these devices. So these are some more details about the metal organic chemical vapor deposition layers. Then we have the molecular beam epitaxy, and the molecular beam epitaxy method basically works by having a fusion cells and then RF plasma nitrogen sources, and then we have ultra high vacuum environment, and then these atoms, we basically deposit these atoms on the substrate to form the epi layers. And again, growth conditions need to be optimized to get good solar cell characteristics. There are other kinds of epitaxial layer growth mechanisms as well, methods as well. Dislocations are centers for recombination. And here we show just a schematic. Actually, the woodsite crystal structure will show differently, but here we show for the cube, this is actually a cubic diagram, but we show the schematic of edge dislocations and skew dislocations that are typically there in semiconductor materials. Now, these induce deep states in the band gap or states close to the middle of the band gap, and these lead to non-radiative recombination, and they need to be minimized in order to get good solar cell efficiencies. Now, we can experimentally determine these dislocation densities in these materials as the number of dislocations per centimeter square in these materials in order to get good device characteristics to understand the growth conditions necessary to obtain the optimal device layers for good solar cell performance. This slide shows schematics of tandem cells. Now, this shows a different material system, but the considerations are very same in the indium gallium nitride system also. But what the important thing to keep in mind is that each subcell needs to be interfaced using these so-called P++ N++ tunnel junctions. These tunnel junctions basically make sure that there is minimal voltage drop when the photocurrent is flowing in these tandem solar cells. So now the thing is in indium gallium nitride, especially at high gallium composition, doping the p-type layer becomes much more difficult, and we'll discuss that more. And so the tunnel junction needs to be optimized in order to get good tandem cell operation. The other thing is there is something called a critical thickness. When you grow these epi layers on a substrate, or one epi layer on another layer, the top epi layer tends to adjust its lattice constant to the bottom epi layer up to a certain thickness. But beyond a certain thickness, when the strain energy becomes high, it relaxes by forming misfit dislocations. And it relaxes to its natural lattice constant. And when it does that, the piezoelectric polarization goes away. So the critical thickness affects piezoelectric polarization. This critical thickness needs to be determined theoretically and experimentally. And so there are theoretical methods to predict some of these critical thicknesses using material parameters. Now, there are models which can tell us what the critical thicknesses are for equilibrium, and they have these various kinds of material and quantum mechanical parameters that go into that. But there are alternative models based on different cases. But we need to keep in mind that non-equilibrium kinetics can affect the critical thickness. So it may not be the equilibrium calculated critical thickness. So those needs to be understood both theoretically and experimentally in order to arrive at best solar cell design. Then there is this Vander-Merwe. So there are these Matthews and Blakeslee model, then there is a People and Bean model, and then there is the Vander-Merwe model. So these are alternative models to help understand the critical thickness requirements and to achieve the best device layer design and device performance. Then we discuss some details about transparent conducting oxides. So we have tin oxide, indium oxide, and zinc oxide. Combinations of these, and those are used to obtain transparent conducting oxides. As we mentioned, there is the plasma frequency, which needs to have a certain sequencing with the photon frequency in order to minimize reflection and absorption. And that is what we're trying to achieve here by using these combinations of these metal oxide layers. These are TCO band structures, and as you know, these band structures determine effective mass and plasmon frequency, and that determines the whether the electrode is transparent or not. And so these band structures go into determining absorption, transmission, and reflection in these materials. So in this slide, we show the absorption coefficient and transmission coefficients percentages in these materials and some of these materials that are used to form the TCOs for the top electrodes in these solar cells. So, okay, a little bit more about so I'm staying on this slide was just because it shows 4 different indium concentrations, and that is relevant because as we go to higher gallium concentrations, this is a slide about absorption coefficient, but I'm talking about a slightly different topic, and that is the electron and hole concentrations that can be obtained by impurity doping or shallow donors and shallow acceptors, and the kind of contacts that can be made for these materials. Remember, there's a top contact and the bottom contact, and contacts have contact resistance. The contacts aren't completely perfect. There is a resistance drop in these contacts, a nonlinear kind of. We try to make it more linear, but there is a resistance drop in these. There is a voltage drop at these contacts due to, and they need to be optimized. Now, typically, the contacts work by having tunneling of electrons and tunneling of holes. If it's N-type, then we have tunneling of electrons across a barrier, metal semiconductor barrier, and if it's P-type, we have tunneling of electrons, of holes. Of a P-type, it is tunneling of holes across the metal semiconductor barrier. Now, the tunneling, has a transmission coefficient associated with it. The higher the transmission coefficient, the better the tunneling, and the lower the voltage drop in these contacts. Now, the transmission coefficient depends on the effective mass of the electron or the hole, effective mass, the barrier height, and the barrier width. Now, the thing to keep in mind is that for the P-type material, it can become difficult to obtain good contacts in these semiconductor systems. So what happens is that the acceptor binding energy in these materials is fairly high, something like 150 millielectron volts, which is much higher than the thermal energy at room temperature, which is 25 millielectron volts. And so because of this 150 millielectron or 160 millielectron volt binding energy, the ionization percentage of shallow acceptors like magnesium in these materials is very low. So to get something like, let's say, 10 to the power 19 per centimeter cube hole concentration, we need to dope to something like 10 to the power 20 or 2 or 3 times 10 to the power 20 per centimeter cube physical doping concentration. Even after we do that, the effective masses for holes tend to be quite high in these materials. They are something like in the order, for electrons, the effective mass is something like 0.2 to 0.3 times the free electron mass, while for holes, it is something like 1 to 1.5 for 2 of the kinds of holes, and then slightly different for another kind of hole. So the transmission coefficient for holes tends to be low. So we may need to do some different kind of optimization, like adding some polarization carrying thin cap layers to induce severe band bending in order to get good transmission coefficients. A little bit about 3 different kinds of holes. So we have the so-called heavy holes, the light holes, and then there is the spin orbit split off holes in these materials. And now the spin orbit split off hole has a valence band maximum, which is slightly below the valence band maximum for heavy holes and light holes. Now the heavy holes have large effective masses, the light holes slightly smaller, and the split off holes tend to have even slightly more small, and they're different effective mass. And the effective mass determines density of states. Now, what this means is that at a specific equilibrium or quasi-equilibrium, there are more heavy holes and less number of split-off holes. And since these heavy holes have large effective masses, that decreases the transmission probability and makes it difficult to obtain good ohmic contacts with these devices. And so those are things that need to be kept in mind in order to optimize solar cell device performance. Also, some more physics involving these spontaneous and piezoelectric polarization. So here we show an abrupt heterojunction. When you have an abrupt heterojunction, there is an abrupt change in polarization as we go from one layer to another, and that leads to so-called bound sheet charge densities at the interface. When we have quasi-continuous or continuous polarization grading, we get what is called bound charge concentrations. Then the divergence of the polarization basically gives rise to a bound charge distributions, and that enters into the electrostatic and electrodynamic equations of the device, and that leads to different device performance. So then those need to be kept in mind and optimized in order to get the best solar cell device performance. Now, as I already mentioned, we can try to have double heterojunction structures with abrupt change in material composition, but there we have abrupt barriers to current flow. And those abrupt barriers can arise for some of the carriers. For example, we have electrons and we have holes for some of these carriers, and we have three kinds of holes. And for some of these barriers, the abrupt barrier can obstruct the current flow, and that is what we don't want to happen. So the quasi-continuous grading is a fairly good way of getting over this constraint and to get good photocurrents, to get good photovoltages, and to get the best solar cell device performance out of these devices. So we need to keep it. And the other thing is that we have what we have discussed is typically for the 0001 axis of these semiconductors, but there can be other combinations for strained, but there can be other, there can be other kinds of growth planes. For example, one can have what is called the 112 bar 1 plane, etc. And we can have non-polar growth planes in this Woodside structure as well. So we have basically three varieties of structures to consider. We have the Woodside 0001, the polar axis, then the Woodside non-polar axis, and then we have the cubic thing. Now, since the Woodside is the technologically most common form of these semiconductors, the non-polar axis become an alternative to consider for getting good solar cell device performance. But again, there is also differences in the technological complexity between 0001 polar C axis or polar axis, and then the A plane and M plane or the non-polar axis. So we have to do the device optimizations and the growth optimizations, and we have to consider all of these in order to get best device performance. So, so the 0001 and the C-axis and then the M plane and the A plane non-polar. So the polar C-axis and the non-polar A plane and M plane. We need to have the right device optimization, and then we need to balance that against the growth complexity in order to get the best kind of option to use for making solar cells out of the indium gallium nitride material system. So that basically concludes our talk about photovoltaics with bandgap polarization and different kinds of materials grading.